All right, so this is take two on our presentation. I appreciate everyone's understanding with the technical difficulties last week. As you can see, we got those worked out here. Just to remind everybody, this is being recorded, so you could come back and certainly check it out later at our website. We will be posting at the end of this a PDH QR code in order for you to get your PDH credit. And um, the final thing is we certainly want to see everybody we can out in the real world events that we have coming up, and those we'll be getting those sent out here as we start the next season. This is our last presentation of the season, so Carlo, I'm so happy to have you here now, live and in person on camera. Um, and we're going to jump right into the presentation. So we're not wasting any time here. So Carlo, I will let you get started. Thanks a lot.
All right, thanks for the introduction. Yes, I'm excited to by the opportunity to talk about this wonderful bridge, in my opinion, and I'm happy we're able to reconnect a week later. But yeah, let's start and dive right in on this presentation. And so a little bit of introduction. I'm an engineer with Atkinson Nolan and Associates. We have two offices, one in Colorado and one in New York. I'm currently in the Colorado office. As a background, I have some experience in non-destructive evaluation testing of historic structures. I have also experience on finite element analysis, both linear and nonlinear, with particular focus on, again, on masonry structures. And then, I work on a regular basis on repair and strengthening design, and of course on masonry arch bridges in terms of analysis and load rating. I'm also involved with the seismic evaluation retrofit of existing buildings, AC 41, with the masonry chapter. Okay, moving on is a quick outline of what we are going to talk about today, what we are going to cover. I'm going to start with a little bit of background on stone arch bridges in general before, talking about the Keystone Bridge. And then we are going to talk about the evaluation, the analysis, the rehabilitation work, and the rating of the bridge. And I hope that I can use this project as an example and expand on some topics that are more general concepts for the assessment and rehabilitation of stone arch bridges. Well, let's start with a simple question, or how many stone arch bridges we have in the US? Well, based on a 2013 bridge inventory, it seems there are approximately 1,700 masonry arch bridges. Now, that includes both stone arches and clay masonry arches. The majority of these bridges are concentrated in the northeast portion of the US and along low volume roads. And if you look at this plot, which shows the number of masonry bridges that were constructed over the years, you see that more than half were built prior to 1920. So it's fair to say that half of the current existing bridges have exceeded their intended service life. But they are still on service. And why? Why they're still on service? Well, there are several reasons why. And let's look at some of them. It could be critical location. For instance, if you look at the bridge on the first photo, as well as the bridge shown on the last photo, these are small bridges on low volume road or county roads. And those are the only crossing for miles and miles. So, if you have to go around, it's going to be a long detour. So it's critical. That's the critical location for them. Then they're still in service because of maybe cost of replacement. For instance, if you look at the third picture from the left, that's a bridge in Massachusetts on Main Street. And well, that's still in place because in the end, it was actually more cost effective to rehabilitate the existing arch bridge than to replace it with a new one. And another reason that these bridges can still be in service is because they find uh, a new use. For instance, the second bridge from the left, it's the Bow Ridge Bridge in Pennsylvania, used to be a railroad bridge that went out of commission and has been repurposed to carry vehicular traffic on, I believe, recreational area. And yeah, here are two more examples of stone arch bridges that are still in service. On the left, we have a bridge in Colorado, and this one as well used to be railroad bridge that went out of commission in the 1960s when it was replaced by a new concrete bridge, reinforced concrete bridge. Now, that bridge became obsolete 50 years later, and so the bridge owner wanted to explore the option of bringing back to service the old stone arch bridge and see if that was an option instead of building a new bridge. And in this particular case, conditions were kind of favorable because, you know, we had a lot of fill over the arches, meaning that the loads spread out very well. And the bridge was in really good shapes, so it only required some repair work, but nothing major. And we were able to bring this bridge back in service at a fraction of the estimated cost to replace it with a new bridge. On the right here, we actually have an interesting example. It's a private bridge, and it's the only way serving the only access road to a property, and which went under a major renovation in the last couple of years. And so the bridge was kind of, the contractor wanted to use the bridge to bring all the construction equipment on site, and some included some heavy truck loads in the order of 25-ton concrete trucks, but they also wanted to bring on site a large crane, construction crane, with a weight of approximately 50 ton. And so we wanted to make sure that the bridge could handle these heavy construction loads. Well, let's get to the Keystone Bridge. So it was built in 1889 in Elkader, Iowa, which is a small town. I think currently has around 1,200 people. And it was constructed to replace a structurally deficient iron bridge. And back in the day, the main reason to shift material and use stone masonry, the main purpose was to have should I say, a bridge that would last a little bit longer than other of past bridges. And so they try to switch material because under the idea under some conditions, stone masonry can last a long time. And in fact, this bridge has been around and for more than 135 years. Now, this bridge, because of its historical significance, is also a part of the historic district of the city, has been listed on the National Register of Historic Places, I believe in 1976. So it's still in service because its critical location. There are only two bridges crossing this river, and so it provides an important access route to the city or the town. And replacing the bridge was going to be quite expensive, and it was not going to be easy because of historical designation. Let's talk about a little bit of the history of the Keystone Bridge. As we said, the bridge was intended to replace some old timber and iron bridges that were built prior to the Keystone Bridge construction, but they first, they didn't last very long. It appears that after a decade or so, they were structurally deficient and they went out of commission. Now, some of the historical background comes out from an article. This bridge was featured in 1891 in an article in the Engineering News in American Railway Journal. So some of these historic photos that you see and this historic background information that I'm giving you, it all comes from that article. It's an interesting article talking about the history of the bridge. In 1888, so the city decided to replace the latest iron truss bridge. I believe that it was structurally deficient, and decided to switch and trying to use stone. And the location was particularly very suitable for the use of stone masonry because there is a shallow bedrock, competent bedrock that can carry a lot of material weight, and there is a nearby quarry where the native limestone can be sourced and brought to site, and so it's a good location to build a stone arch bridge. However, two bids were requested, one for an iron truss and one for a stone arch bridge. And actually, it's reported that the stone arch bridge was cheaper to build, and the project was awarded for roughly $13,000 back in the day. So the design, the bridge was designed by a local engineer out of Dubuque in Iowa, and the design called for a double arch structure with each arch approximately 3 feet in thickness at the crown section, and with the thickness increasing to 4 feet at the spring line. That's the location where the arches meet the abutments. The span was approximately 84 feet in the design with a clear height of 28 feet. And the clear width inside the parapets was 30 feet and accounted for a 24 feet roadway plus a 6-foot wide sidewalk. But, let's how were these bridges designed, right? They're more than 100 years old, and sometimes it's interesting to think about the design process of these old structures. Well, we don't know for sure, but it's likely that the design would follow these steps. The first one is select an arch geometry. It could be either circular or elliptical, and circular being the most popular. And then the next step will be to use some empirical rules to, define the geometry of the arch in terms of the thickness based on the span, or define preliminary size of the abutments. And for example, here, according to one of these empirical rules, which is highlighted here in blue in the blue box, the depth of the keystone of the stone at the apex of the arch is a function of the arch radius, the span, and then an arbitrary constant. And then if we apply this rule to the Keystone Bridge, we come up with a thickness, with a crown thickness of 2.6 feet when using first-class cut stone, good quality stone, or 2.9 feet for second-class cut stone, which is, not too different. It's pretty much in line with the actual thickness of the bridge at 3 feet. So the next step would have been to check for stability, check the stability of the arch. Now we have our geometry, and we have to make sure that the arch is stable based on the geometry that we have selected. And usually that would likely have involved a graphical analysis where we throw the thrust line, which is the location of, of the compressive forces through the arch thickness along the arch profile. And then it's accepted basically that if the truss line falls within the middle third of the arch cross section, the arch is stable. But we can also use the graphical analysis to estimate reaction forces for the foundation design or the horizontal truss at the crown. Now, the last step would have likely been a stress check to make sure that the maximum stresses in the arch are below the allowable values. And specifically to the Keystone Bridge, some details about its design became available when the engineer presented a paper to the Iowa Civil Engineering Association back in 1889. For instance, it's reported that the horizontal thrust was estimated at 65,000 pounds per foot. The engineer assumed an allowable compressive stress for the limestone of 150 psi. And then based on the two, we can calculate the keystone depth. The thickness of the arch at the crown was calculated at 3 feet. So what construction of these bridges was not easy. And as you can see on these historical photos, it would require, the use of centering, which is the temporary support. It's a timber support that it's used to during the arch construction, and it's used to support the stone, essentially the stone masonry as it gets built from the spring lines up to the crown section. So in this case, we believe there was, only 5 frames were used at a space of 7.5 feet on center, and it was reported that just some information that 50,000 feet of lumber were used, and for the centering, the construction of the bridge, approximately 4,000 cubic yards of materials were used in the bridge construction. The weight of the bridge was estimated to be around 18 million pounds, and the construction started in 1888, and it lasted actually only 10 months, which to me is remarkable, given the means and methods of construction available at the time. The total construction cost, of course, the bridge, the construction went over budget because the total construction cost ended up being a little bit more than $16,000, which, if my conversion is correct, that equates to roughly more than $500,000 in today's values. So let's move on to the next section of the presentation, and let's talk about the evaluation of the bridge. So with the condition of the bridge deteriorating over the years, I think in 2015, the city started planning a renovation to extend the bridge service life and open the bridge to all vehicle traffic. And in fact, the bridge was posted because of the continuing deterioration, and the bridge was posted at 5 ton. And so, all the commercial vehicles couldn't drive over the bridge anymore. They had to take a long detour. But anyway, we started our evaluation by reviewing all the existing documents that were available and related to the construction of the bridge, and documenting past repair campaigns. And all these documents provide valuable information for future analysis and rehabilitation work. So for instance, we were able to find, the drawings that, tie rods were installed at some point. We don't know, we're not sure exactly when, but they were installed in order to tie the spandrel walls together. And then when in 1972, a new sidewalk was added to the exterior of the bridge, cantilevering off one of the spandrel walls, we found documentation that the outer sections of those tie rods were replaced with larger diameter rods. And then there was a record of extensive repointing that was done in 1974, which included also repair or repointing of longitudinal cracks below the arches, right below the in the arches, right below the spanker walls. This is actually important because I'm going to show some photos of these longitudinal cracks that are still were still an issue in 10 years ago and prompted the lower posting of the bridge. So they were pointed back in the 70s, but you know they were not fixed. The underlying cause of those cracks was not fixed. So as part of the evaluation, we also conducted, you know, a bridge survey in order to establish the geometry and dimensions and have some base drawings for in order to develop construction drawings. As part of the assessment of the evaluation, we conducted a condition assessment of the bridge, paying particular attention to existing damage conditions because they have an impact on the structural capacity of the bridge, but also, you know, to estimate, have an idea of the extent of repairs that were needed. And at the same time, we collected some material samples, stone and mortar samples for material testing in order to establish some basic mechanical properties. So we conducted a condition assessment of the bridge. We found that the bridge, the stone masonry, was a kind of in fair condition overall, but there were some areas of cracking and spalling of the limestone. Those were actually concentrated, interesting enough, on the south side of the bridge. And, you know, this type of spalling is usually associated with freestyle damage. And, you know, the locations that have a south exposure are more prone to this damage because you know, those are the locations that experience large swings in temperatures, even in winter. So the material gets wet and it freezes overnight, it thaws during the day, and you know, the phenomenon produce damage in the limestone. There were some longitudinal cracks on the underside of ridges. Some cracks almost ran the entire length of the bridge, but they were narrower at the spring line and wider as we would approach the crown or the apex of the bridge. There were also signs of water stains on the underside of the bridge. That's an indication of water seeping through the roadway and through the fill material and reaching the arch. And that's not a good thing because, you know, it's an active source of moisture that is going to feed the damaging freeze-thaw cycles that produce all this material damage. Now, it's one thing to extend the longevity for these structures. It's really important to, you know, keep these arches dry as much as possible, give them an opportunity to dry, and that starts at the roadway level with a good drainage plan. So as we said, with the conditions deteriorating and deteriorating fast, so the bridge was without, you know, a structural analysis done in the past, I believe 15, 20 years. So the bridge was posted at 5 tons until, you know, we could take a look and implement some repair work and do a final rating. So let's talk a little bit more about these longitudinal cracks on the underside of the bridge. And these cracks are common on the, it's a common issue for these structures. And why do they form? It's not, you know, there are some research, some studies out there that point to the direction that, you know, There is a mismatch in bending stiffness in the arch itself as you go from the center of the arch to the edges of the arch. That's because when you get to the edges of the arch, you have the added stiffening or the spandrel walls contribute and make the arch a little bit stiffer at that section. And so the arch deflects less compared to the to the sections that are away from the spandrel walls. And also there are some studies that indicate that there are some secondary bending stresses that tend to develop a put the section of the arch intention in the transverse direction. So when you put all these things together, basically, the arch cracks tend to form at that particular location. I've seen those cracks on almost every single bridge that I've looked at. As part of the evaluation, we also did some surface penetrating radar, SPR scanning of the bridge and the spandrel walls in order to evaluate the stone thickness and solidity of the stone masonry. Now, why this is important? Because as a, especially for the thickness of the arch, that's a parameter that you need for the structural analysis. And you can measure the thickness at the face of the arches, but there is no guarantee that that's the thickness that you have elsewhere in the arch. In fact, if you look at these historic photos, you can see that they use nice dressed stones at the at the face of the arches of the parallel bolts, but as soon as you move away, the thickness of those units it changes considerably, and it's just how they constructed the arches back then. And so we use radar in order to confirm, first of all, that the thickness the same as that we can measure at the arch face, but also to look for potential damage and loss in cross section in the arch as well. So really quickly, for those of you that are not familiar with this approach, surface penetrating radar, also known as ground penetrating radar, uses reflections of microwave energy to identify internal anomalies. So as the radar antenna goes across the surface of our wall or arch, it propagates into the masonry, and portions of this energy is reflected back and collected by the radar device. So anytime energy is reflected back, it leaves a distinct reflection in the radar trace. And those are the parabolic or flat lines that you see in the bottom of the figure. And we are going to see some of those in an actual radar trace in the next slide. So now, as you can see, radar scanning comes with some challenges because you have to reach the underside of the bridge. And at the top, I have a photo here, which is not from the Keystone Bridge, because when we did our survey, we didn't have a drone on site, but this is from another bridge, and it gives you the idea of what it takes. So you need an inspection vehicle in order to reach the underside of the bridge and do your scanning. The additional challenge with the Keystone Bridge was that, as I mentioned, it was posted at 5 tons, so we couldn't position the inspection vehicles where we wanted to do a comprehensive or to investigate the entire bridge. I mean, we although the design team was comfortable, driving a little bit over the bridge, the company providing the vehicle wasn't comfortable, and for good reasons. They had their own reasons. So we could only access the bridge from, similar to these photos, from parking the vehicle near the edges of the arches. But nevertheless, so we are able to connect some data, and one key finding was actually that the thickness of the crown of one of the two arches was was 29 inches instead of 36 inches. And that's a 19% reduction in arch thickness, which, arch thickness is one of the main parameters that define the capacity of these extractions. As you can see here in this bottom left image, that's a radar trace that was collected on the bridge, and it shows in I don't know if you can see the yellow dashed line. That's the back of the arch, because we were scanning from underneath. That's the back of the arch, and you can see that back of the arch line is not continuous. It breaks, and it means that there is some reduction in arch thickness. And then there are also some voids in the fill behind the arch. But the main finding was that there were some areas where the arch thickness was less than what we could measure at the spandrel walls, and whether that's for maybe due to material deterioration, or because small thinner stones were used in the original construction, or a combination of the two. Yeah, we don't know, but for sure we have some less material than we wanted, or we were accounted for. Now, because this was actually a critical finding, we also wanted to double check the radar investigation results, and so we did some cutting from the roadway down to intersect the arch and take some direct measurements. Well, let's talk a little bit about the analysis of these structures. What options we have? Well, there are a few options. We can use empirical methods, which are conservative in nature and should only be used as screening tools. There are also other methods like plastic limit analysis, and that are more appropriate, but they still have some limitations because they're based on a 2D approach, two-dimensional approach. And then we have the finite element method, which it's fair to say it's the most common among engineers. And within the finite element method, we have the option of doing one-dimensional analysis, a frame analysis, a 2D analysis, or build up a 3D model for a three-dimensional analysis, as you can see in these images here on the right. They all come with pros and cons, and it's easier to do a 1D, 2D analysis, but they could because you have to make some assumptions. They could result in some conservative rating compared to a 3D analysis, which it takes more time to implement. So one of the challenges is actually in this base by project by project basis. So it's try to find a cost-effective solution that does not produce conservative ratings. So I think that's one of the challenges engineers face when look at these structures. Well, for the Keystone Bridge, however, because of its historic significance, we decided that full 3D analysis was the most appropriate analysis method. So we built the full 3D model that you can see here by modeling the arches, the foundations, the spandrel walls, and the fill in between. The 3D analysis allowed us to, account for the complex geometry of an arch bridge, but also for different loading conditions. We were able to look at the lateral load distribution of through the fill material, and we can use the 3D models to look at the pressure on the spandrel walls and see if we need tie rods to tie the spandrel walls together, and we can use the model to look at construction sequence and different construction loads, and we have some example of that coming up. So in terms of lateral load distribution through the earth fill, I want to talk a little bit about it because it's important. You have an arch with a 3D structure. we cover it with fill, and then you ask yourself how much of the wheel load is going to reach the arch structure, and how is the load spreading through that fill material. And because the fill material varies in depth from the crown to the spandrel walls, you engage different sections at different locations. So one option is to follow the AASHTO standard, and it lets you use a lateral load distribution at a slope of 1.14 vertical to 1 horizontal, and sometimes this may be conservative. In fact, if you another way to look at the this lateral load distribution is that if you do a live load test of your bridge, you can actually use the data that you collect during the test and look at the deformation of the arch under a known vehicle and come up with an equivalent lateral load distribution based on the displacement curve and the peak displacement that you measure, the peak deformations that you measure during the test. So for this particular instance, we were able to find that the distribution based on the live load test is the one shown in blue, and you can see it's a little bit wider than the one that you get following the AASHTO standard. And I think I have to apologize about the light going on off all the time, but it's based on a motion sensors. I think I need to move my arms a little bit more. Anyway, going back to the bridge. So if you happen to do a testing of the bridge, you can use the data that you collect to come up with an equivalent lateral load distribution. Or if you end up doing a 3D finite element analysis, you can also evaluate, the lateral load distribution based on your compressive and tensile stress profile that you have on the section that you are reading. And that's another advantage of using a 3D model. Now, we talked about, I just mentioned that, we also use the model to investigate the proposed construction sequence and construction loads. So for instance, the rehabilitation design called for a new concrete deck and a two-stage construction sequence. So there was a concern that, the construction sequence could overload the bridge because every time you remove fill only on a portion of the bridge, you create an unbalanced load condition, and it could be that you overload a portion of an arch in tension. And so we use the finite element model to evaluate the contraction sequence. As you can see on the right side, there are two cross sections. The one at the top is, let's look at a load case when one lane is excavated and there is some construction equipment in it. In this case, I think it's a dump truck with a small backbow operating behind it, while the other lane is open. And then the second load case at the bottom shows where the new concrete deck is in place on half of the roadway and construction is happening on the other half of the roadway. And another construction load that we wanted to explore was that the contractor had the need to use a larger excavator. I believe this one was around 38,000 pounds machine. And again, the main concern was really with the unbalanced load and having that excavator operating on a section that was didn't have much fill over the arch. And the concern was really with the tensile stresses shown here in this picture on the right in red in the transverse direction at the bottom of the arch, because we know that those stresses could produce some longitudinal cracks in the arch. So we did our analysis, and it's actually nice that you can see the equipment on the bridge on the left side and our simulation on the right side. And then based on the anticipated level of stresses that we were seeing in the analysis, we decided to limit the location where that particular excavator with that particular weight could be operated on the bridge. And as part of the bridge analysis, no matter what analysis you do, you need to account for some material properties, which, for these type of structures, they're difficult to obtain. I mean, you can sample some components like stone and mortar and do some testing, but you cannot test the assembly, the actual stone masonry. The manual for bridge evaluation has some allowable compressive stresses for different type of stone materials, but there is no values for allowable tensile stresses or elastic modulus, which are other materials that we use in the analysis, and there is no direction on what to do to test for them. Not to mention the soil, which is never tested for analysis purposes. And so the option is, do the test that you can, and then implement or base your material properties that you cannot test based on typical published values. Okay, so let's move on the bridge rehabilitation work that was done. So the existing deck was, we had 2 inches of asphalt over 2¼ inches of brick over 5 inches of unreinforced concrete over fill. So that was not a structurally sound deck. So we decided to replace it with a 10-inch reinforced concrete deck over a total of 8-inch sub-base and backfill. The good thing about having a new concrete deck is that also it helps with the lateral load distribution and is going to engage a larger section of your arch. It's going to help with the rating of the arch as well. So the old cantilever sidewalk was also replaced with a new one, still on the exterior of the bridge, cantilevering off one of the spandrel walls on the north side. And so here are some construction details. Shear was transferred directly by bearing on the stone masonry, but it's a cantilever structure, so the tension compression forces reactions were carried by a strut and tie approach with new tie rods that were encased in concrete, as you can see on some of these photos here. As far as masonry rehabilitation work, we did a lot of repointing in order to address the mortar deterioration or cracking. But because this bridge is listed in the National Register of Historic Places, we had to follow the provisions of the Secretary of Interior Standards for Treatment of Historic Properties, which means we had to do testing. We had to test the existing materials in order to select compatible replacement materials. So we carried out a mortar analysis in order to identify a compatible mix. We also tested the stone for the replacement stone. We tested the new stone, which all this replacement stone on this project came from the same local quarry that we believe was used to source all the stone for the original construction. So in terms of stone repairs, the main one was that stone attachment, when you basically remove all your damaged material and you chip back until sound material, and then you basically put in place, new stone is keyed in place into the existing masonry and secured with stainless steel pins to facilitate and improve the mechanical interlocking. And then we had to deal with the longitudinal cracks, right? We know that these cracks were reported in the past, in the 70s, but they came back because unless you address the underlying condition, they're still coming back. So our approach was to do some arch painting, so that it means installing some longitudinal cracks in the arch barrels, and that would tie the side of the arch back into the arch. So these anchors are very common in masonry rehabilitation projects and strengthening projects. So the anchor itself is a stainless steel threaded rod, which is enclosed in a fabric sock to contain the injection grout. So these anchors are used for structural connections in masonry or for improving the capacity of the masonry walls as well when they're installed in the horizontal vertical direction. So it's a good product for stone arch bridges as well. So the way that we implemented our repair work was the coral, they're installed from the side of the bridge, coring horizontally and, installing the anchors that are then, which are then grouted in place using high strength cementitious grout. For this particular bridge, I think we installed these anchors at 4 feet on center along the length of the arch. And, essentially we are trying to bridge the crack and tie the two sides of the masonry on either side of the crack and reinforce the portion of the masonry across the crack. And these anchors also will provide some, or will enhance the flexure capacity in the transverse direction of the arch, which as you recall, we discussed that early on, and it seems to be one of the causes of these cracks. Now, well, we were not anticipating this, but we ended up replacing a number of whole stone units. So what happened was that when the contractor removed the tie rods, essentially one of these longitudinal cracks started to open up, or that's what they said, that's what they observed. So we took a look, and well, maybe the portion of the masonry that was touching moved a little bit outward after the tie rods were removed. The bottom line is that there was a lot of material deterioration and damage, and in the crack themselves, because they over the years that stone kind of got wet, got through freeze-thaw cycles, got damaged, and as soon as they removed the confinement that was provided by those tie rods, all that material came loose. But we took a deeper look at those stone units that you see at the face of the arch, and they were really in a bad shape. So we had to replace 5 units, which, due to the location of these units, which are close to the crown of the arch, we had to install some temporary shoring. Well, we did an analysis. We had the model, so we used the model to do a load analysis and provide the loads for the temporary shoring design for this. So what we did was dividing the arch in small 4-foot sections and calculate loads on each section. And because it's an arch, you have to provide support in both the lateral, the horizontal and vertical direction. So you have 2 directions to support. So as I said, we use the finite element model in order to, really be as precise as possible, and in order to optimize the design of the shoring, because, this was an unforeseen cost. So we were taking all the steps that we could to optimize that design. The temporary shoring design was a delegated design, so we provided our shoring loads that we needed, and then the shoring engineer came up actually with a triangular steel frame with the addition of a curved section at the top following the arch profile, which is not that different from the original centering that was used for the construction of the bridge. And we actually only needed two frames spaced at 4 feet apart to support just the outer edge of the arch. Here are some photos of the stone replacement and the installation of the shoring. The contractor actually had to divert water in order to have a dry platform for the shoring installation. They put the shoring in place, removed the stones, and I think they lifted the new stones in place with just a forked lift. Here are some close-up photos of the actual replacement work. You know, you don't realize until you get close enough to see that the gaps that you leave by removing some of the stones are quite large. So there was some additional localized shoring that was needed to support the spandrel wall above while these units were put in place. I believe in these center photos, they are kept in place by shims before the joints in between the stones can be grouted. And, you know, the stone faces also had to be retooled to match the texture of the surroundings units. So finally, let's touch base quickly about the load rating analysis that we did. For arch bridges, what we do is following the Ashton NBE, which, you know, the rating is done at the inventory level only, which is the level of loading that the structure can sustain for an indefinite period of time without experiencing damage. And so it's for the approach follows the allowable stress design by limiting the the maximum tensile compressive stresses that develop the extreme fibers, and make sure that those are under allowable values. One approach is, the use of an axial force bending moment interaction diagram, and at the very least, the minimum rating sections that should be considered are the spring lines, the quarter points, and the crown section. So we ended up using an allowable inventory compressive stress of 325 psi, which I don't know if you recall, but I mentioned that in the original design they used 125 psi. Probably were on the conservative side, but this is a little bit higher than that, and also it reflects the improved condition of the stone masonry due to all the repair work that was carried out. In the final rating, we still decided to use a condition factor and a knowledge factor less than 1 because, well, even though we did a lot of work, we looked at this bridge extensively, there were some, there were still some unknowns, like we didn't know anything about the foundation wall. And it is likely that even though we did a lot of repair work, all that work was done on the exposed face of the arches in the spandrel walls. So it's likely that there is some material deterioration on the soil side of the arch that we are not aware of. And then while we did some material testing, it was limited material testing, so we had to make some assumptions on other material properties. So I think it was reasonable to use values less than 1 for condition factor and knowledge factor for this analysis. We ended up looking at 3 different load conditions for the load rating to account for different locations that the vehicles can be within the roadway. On the top, you see load case number 1, where the live load is close. It kind of, it's you have given the width of the bridge, you have 2 traffic lanes. So load case 1 gives you the condition where the live load is close to each. The 2 tracks are close to each other on the traffic lanes. Load case 2 is basically overloading the edges of the arch, and load case 3 is meant to produce an eccentric load on the arch. So we did the load rating for a number of vehicles that were required by the Iowa DOT. So we looked at the standard HS20 plus all the legal loads that are listed here. And we found out that the controlling live load was the HS20 and produced a rating of 4.5, which, yeah, it was good to see that high rating. And the controlling rating, I think, was the crown section of one of the arches with the track positioned in a way to produce the maximum tensile stresses at the bottom of the arch. All right, and that takes us to the end of the presentation, and see if we have any questions.
All right, it looks like there's a couple in the chat. First, masonry prisms can be tested if enough samples of stone are available and an appropriate mortar is used. If not, what masonry strength did you use?
Well, what we did was we tested the stone, the limestone itself. We couldn't test the assembly because the panels are, or there is no easy way to do that in situ. So we collected some stone samples and tested them in comparison in the lab. That gave us a baseline for the existing material that we have, and then we went back into the MBE and trying to see where we landed that table and trying to extrapolate a reasonable allowable compressive stress value for the analysis and design. And also we did some mortar testing, and using that information as well, we knew what type of mortar is in the bridge, what type of stone we have, and so we, based on there is some engineering judgment that goes into that, basically, yeah.
Next question is 325 PSF allowable masonry strength chosen arbitrarily.
Not entirely, but the starting point again was the material testing and the published value in the MBE for limestone and for the particular coursing of the bridge, and then it was increased based on engineering judgment and based on accounting for all the repair work that we have done on the bridge. But yeah, there is no, unfortunately, a direct way to test for compressive strength of the assembly. When I say assembly, it's the masonry that includes both the stone and the mortar joints.
All right, next question. How are the pre-stressing rods designed based on tensile stresses taken from the FE model?
In part, yeah. It was mostly based on hand calculations, but then the actual loads in those rods was verified using the finite element model.
Okay, next question. What did you measure under your load test?
Well, we didn't do, sorry if I gave the wrong impression, but we didn't do any load testing for this particular bridge. The example that I showed in one of the slides was from a different bridge. Just an example and how the test data can be used for calculating an equivalent lateral load distribution.
Okay, and then last question. How come you were able to test stones in mortar but not stone prisms?
Well, it's primarily due to the size of these units. These units are, well, if you think of the thickness of the arch is 3 feet, so that's the width of or the depth of the stone. So and then the stones are roughly on average 20 inches thick, and they extend 5 to 6 feet into the arch. So sampling actual stones is not as easy as it may sound when they're this big. If it, in masonry construction, in a masonry wall, it's easy to remove small prisms because the units are much smaller, but not in this case, in this type of construction where the stone units are much, much larger. So removing actual prisms, it's not feasible. And one option would be, trying to reproduce that construction on a smaller scale in a lab. Especially, you can remove small sections of or smaller units from the spandrel walls, or if you can source the original stone or the replacement stone, you can use that to build small prisms in the lab and test prisms in compression. That would get you close, but then I think close enough, but you have to account for the aspect ratio, because what you test in the lab, it's going to be smaller than what you have in the actual arch.
Awesome. All right. Thank you so much, Carlo. It was a great presentation. I did post the PDH link in the Q&A chat for everyone to see. And it looks like Justin just stuck it up on the screen as well. You can also scan that. Like we said before, the presentation will be posted on our website, and keep a lookout for any upcoming events that we have. Right now, the season is winding down. This was our finale of presentations, I would say, for the 2024-2025 year. So keep a lookout for stuff to come in this coming fall.
Thanks, everybody.
Thank you, Carlo.